Recording now.
Right, okay. So whether or not you'll be allowed to record meetings going forwards is under active consideration at the moment.
Okay. Yeah.
The answer is likely to be no, you will not.
Okay.
But that decision has not been taken yet.
Okay. That's fine.
I will explain why if and when I issue the decision. Okay. Well, it's 1 minute past, so I think we need to start. Can I remind you that these meetings are being assessed, and therefore, and you should we'll give you your assessment in 2-week blocks. So we'll give you last week's assessment and this week's assessment a bit later in the week. All right. Number of marks is not huge, so don't get too worked up about it. But it is also some kind of feedback as to how we're seeing your contribution to these meetings, and that's, of course, there are lots of other ways of getting marks. So, it does give you an incentive to participate. So I will try and go round and give everybody a chance to participate, but better to say something than nothing. All right. So I'm going to start by discussing the component list. If I can find it somewhere. That's the BFD. Right. Okay. So this is the component list that you sent me. First of all, please note it does not say which group. There's no person's name attached to this. There's no date attached to this document. Okay, these things need to go on the document. It's just standard professional. Right.
So okay.
What data you asking for, Dr. Top? As temperature.
Name of the group.
Oh, okay.
Person responsible for the document and the date.
Okay, sir.
Okay.
Yeah. So, you, like many groups of students this year, have decided that when we asked you for a list, we didn't mean a list, we meant several lists. Okay. Now, the purpose of this list is to make up the list of components you're going to put into ChemCAD in the order in which they need to go into ChemCAD, and we recommend boiling point order. You can only do that if you have a list of components that is one list. Also, sulfur 2 turns up in 2 places. Okay, and similarly here, that's 2 components, but it's 1 line. So this list needs improving a bit. Okay.
Mm-hmm.
I've got some comments here. Yes, these deserve a separate line. For some reason, S6 didn't appear. Would somebody like to tell me why S6 does not appear in the component?
We were not sure because when we had the first meeting, we remember Dr. Torp saying that S6 is highly viscous.
Yes.
And we thought that we might not want that one as our product because we couldn't figure it out if we maybe can find a solution of dropping the temperature for S6 to be a useful liquid instead of be as viscous. That would be a problem for us. So
how do you stop S6 from forming when it naturally forms?
Not to stop S6, just to drop the temperature that, because at 160 is when it's highly viscous. So we thought of maybe having an idea of dropping the temperature so that it becomes like.
And halfway down your heat exchanger, where the temperature is intermediate between coming in and going out.
Say that again, sorry.
Well, you've got a condenser, right? It goes in hot, comes out cold, right? In the middle of the condenser, the sulfur temperature is going to be in between hot and cold.
Oh, okay.
Yeah.
Yes, sir.
So, okay. I sort of quite like the idea. In a way, can we avoid having S6? But even at say 150, there is some S6. Okay, but it's mostly S8.
Okay.
right? But there's still some SF6, and so you know, in order to get the thermodynamics right and the temperature profile in your condenser right, you need the S6. And if you don't get the temperature profile in your condenser right, you won't choose the right area, and the condenser might not work.
Right. Right.
So no, sorry, you can't get away with that.
Yeah.
You need to include it.
Okay.
All right.
Yeah.
Yes, sir.
Right. Where was I? What did it say? I'll send you this document afterwards, by the way. And that's one of the reasons why we might not be doing the recording, because you know we'll be sending you information the old-fashioned way. Yeah, I already said that.
So apart from that, everything else is correct in the component list.
Oh, no, I'm not certain. No. We don't check things for you.
Oh, okay.
Oh,
At no point do we check anything for you.
Right.
It's your design project.
Wow.
Okay, I'm giving you feedback.
Feedback. Yes, sir.
Yeah. Okay. What is the definition of a catalyst? Who'd like to give me a definition of a catalyst?
So catalyst speeds up reaction by finding an alternative pathway.
Okay,
So it increases the rate of
that's,
reaction.
Okay, thank you for that, Jason. I'm struggling here with my. There we go. Okay. Yeah. Okay. Anybody else like to give me a different or an additional bit of information about catalysts?
It works by. Oh, sorry.
No, go ahead.
Oh, I was going to say that.
Okay, let's go around. Jared.
I was going to say, in addition, you could. It lowers the activation energy. That's how it finds an alternative reaction pathway. So.
Well, it's more the other way around. The alternative reaction pathway means that there is a lower activation.
Yeah.
Okay, but the two are related. Anybody, Ken? Anything else you'd like to add?
No, sir.
No. Okay. Christian.
That's pretty much what I was going to say as well. Nothing.
We're not hearing you, Christian. You need to be louder.
There's nothing.
Nothing else you'd like to add?
No,
Okay.
nothing much really. Nothing.
Okay. Anna.
Nothing much to add. Yeah.
You're muted, Anas.
You're muted, I'm afraid.
Yeah, I'm saying it's all the same. I was going to say the same. I don't really remember anything else.
No. Okay. Haroon.
Yeah, that would be it, I guess.
That will be it as well. Okay. So none of you think that catalysts, for example, are not changed by the reaction. So in doing the reaction, the catalyst
It doesn't
itself
get used
is not
up.
changed.
It doesn't get used up, but it doesn't
Get
affect
used up, right? Okay.
Yeah.
Now this aluminium oxide catalyst, it's not an aluminium oxide catalyst. It's a catalyst supported on aluminium oxide, but nonetheless, what kind of a catalyst is it? Is it a liquid phase catalyst or a solid phase catalyst? Jason.
Not sure, sir.
Not sure. Jaren.
I was going to say a solid base catalyst.
Solid phase catalyst.
Yeah.
Very good. Catalyst pellet.
Pellet, yeah.
Pellet's okay. Yeah.
Okay.
So,
if it's a solid catalyst, right, and it's not being changed by the reaction, right?
Yeah.
It just sits there, doesn't it?
Yes, sir.
Yeah.
So what's the flow rate of catalyst, Jerry, in your process?
Wouldn't it just be zero because it's stationary?
So it would be zero,
Yeah.
right?
Yes.
Okay. Ken,
Yes, sir.
how do you put a zero flow rate into ChemCAD or HISIS?
How do you put a zero flow rate on chemical
Yeah.
analysis? On HISIS, you could go for. There's a part of the HISIS on the interface that allows you to play with the flow rate of the feed, so you can set the value over that.
Right. Consider every component in HISIS.
Mm-hmm.
Most of them have a zero flow rate in your feed.
Mm-hmm.
right?
Yeah.
So what do? Do you include them or exclude them?
You have to include them.
Yes,
No,
increase.
you don't.
You'd have to yeah.
I would have to.
When you set up a component list in the simulator, do you load all of the components in the database or just the ones that you need?
Just the ones you need.
Ones we need.
Just want the ones you need, right?
Yeah,
Okay. So
yeah.
why do you need aluminum oxide?
Or in this
Yeah,
case,
we don't need. Yeah,
we don't need.
because it's
You don't
stationary.
need it.
Yeah.
Yeah.
There's no flow in. There's no flow out. There's none
Yeah.
made. There's none destroyed. You don't need it.
It stays there. Yeah.
Okay. You don't need it. All right. Okay.
Sorry.
Who,
Can I ask a
who's
question?
next? Yes. Go on then, Ken. Ask a question.
If aluminum oxide is not going to be used in the reaction in the process itself, so are we still going to use a catalyst when it comes to the catalytic stage?
It's
Yeah.
still there.
Yeah.
It
Still
just doesn't need to be in your simulation.
Okay, got it.
Please don't make the mistake of thinking the simulation is the design,
right.
or
Mhm.
even that the simulation has a one-to-one correspondence with the real flow sheet.
Mm-hmm.
None of those things are true. The simulation is just a sophisticated calculator.
Right.
You don't need to do any calculations about destruction or flow of the catalyst.
Okay.
Okay.
You will need to do a very quick calculation as to how much it costs to buy in the first place, but that's nothing to do with the steady state simulation, is it?
Yeah.
Okay. Christian,
Yes.
which amine are you intending to use in your absorber system in the Scott press?
I'm not sure which one it is.
You're not sure which one it is. Anas,
Yes.
which amine are you going to be
Which
using in the
amine?
Scott process?
Well,
Uh,
I think it's ammonia.
No, it's not.
It's ammonia.
Anas,
actually, no. I don't think we discussed it. But what
okay,
kinds
all
of
right.
amines are?
Hopefully somebody will give me an answer. Harun?
Monoethanol amine.
Okay,
MEE.
all right. Harun, that is at least an amine. But
Pardon?
it's the wrong one.
There is also DEA, but I read upon MEA being a more better one out of the two, if I'm not mistaken. That's what I read.
Well, it depends.
Yeah,
What criteria are you judging it by?
fair enough. Yeah, I
Mhm.
guess so. Yeah.
Well, no, you're the designers. You tell me what criteria you want out of your amine. Now, if we go to the block flow diagram, we might be able to discuss that.
Yeah.
Okay.
Yeah.
Now, look, there are trivial points, there are important points, and there are things that are really quite difficult, quite advanced, and are crucial to the design. And this is one of those in the last category. Okay, so pay attention with respect to this because this is important. So you're presumably still seeing that particular. Are you still seeing that document or not?
I can share
Are you still seeing my document?
I can't see any.
No.
We
No,
can
you
not
can't see any document. Did you
Yes,
ever
yes.
see any document?
No, no.
No. Okay, all right. My apologies. It's all right. There wasn't much to see.
Oh, right.
But you do need to see what I'm. You do need to see now. Can you see your block flow diagram?
Yes, sir.
Yes.
Good.
Yeah.
Let's go along to here then. We're talking about this part here, aren't we?
Yes, yes.
Yeah.
Okay. So where have we got to with the list? I think probably
Absorbers.
we would.
Absorb.
That was Ken, was it? I don't know. Or Harun.
Harun.
Okay, let's go. So Jason, what is in this stream here?
So you
In
got
I just want the major components.
so you got the SO2 being absorbed by the solvent that enters. So like if it's the MEA, so you got so from the quench column, because from the hydrogenation reactor, you form the H2S. So the H2S gets cooled by the waste heat boiler, the quench column, then it gets further absorbed by the solvent.
Okay, you're being a little bit incoherent here. Can you just answer the question, what's in the stream? You seem to suggest that SO2 was in that stream, is that right?
No, sorry, H2S.
H2S.
Yeah.
Good. All right. Jerin.
Yep.
Can you name something else that's in that stream?
There would be carbon dioxide in the stream.
Carbon dioxide. Very good. Excellent. Marvelous. All right. And I will nominate nitrogen.
Okay, alright, yeah.
Okay.
Yes, sir.
Yes, there was some nitrogen came in with the air, wasn't it? Okay. So let's just think about those three things. All right. Now, two of those things are called acid gases. Okay. And what an amine does is it captures acid gases. And the two acid gases are hydrogen sulfide and carbon dioxide. And MEA is very good at capturing both. Ken,
Yes, sir.
where do you want the hydrogen sulfide to go?
What's gonna happen is it's not gonna be able the amide itself, even though it's gonna separate both, but it's not gonna be
Okay.
able
Ken,
to.
listen to the question, please.
Yeah. Okay.
Okay.
Goes off. Go
Where
off
do you want
incinerator.
it to go?
Off the incinerator gas.
No.
So-
You want it to go this way and get recycled back to the front of the process.
Okay, sir.
All right? Because your process is about turning hydrogen sulfide into sulfur.
Okay.
If you send it the other way, it gets burnt in the incinerator and gets turned into SO2. What happened there? I wanted to do that. Let's see if that's true. Yes, there it is, incinerator.
Mm-hmm.
Right?
Okay.
You want the H2S to go this way, and then it gets recycled down that line there. Okay, so who is after Ken? Anas,
Yes.
where do you want the carbon dioxide to go?
Into the incinerator.
Into the incinerator. Why do you want it to go that way and not the other way?
Because you don't need it to be recycled. No, you're not getting anything out of it. You just want to vent it out.
You just want to vent it out because there is nowhere else that it would come out. You need to let it out. Right, okay, so they're both acid gases. They would both be captured by MEA. Do you want to use MEA?
No.
No. You want to use an amine that will capture hydrogen sulfide and will not capture carbon dioxide.
Okay.
Ooh. Who has been to the literature to look for that particular amine?
No.
No, because you didn't know to ask the question, did you?
Why would we not want to capture acid gas? Carbon dioxide, because if we were to vent it out, doesn't that contribute to global warming? And
Yeah.
It does. Of course it does. But what else are you going to do with it?
Carbon capture.
Carbon capture, but you're here capturing a mixture of hydrogen sulfide and carbon dioxide.
CO2.
So then you'd have to separate them again.
Yeah.
And what you've got to always remember is that in chemical processes are much smaller than power stations. Right?
Right.
So we are allowed, at least at the moment, to put carbon dioxide into the atmosphere because in terms of addressing the big emitters first, it's not going to be the chemical industry. Well, certainly not little streams from chemical processes like that. power stations are the biggest emitters. Therefore, that's where it's going to be cheapest to do something about it first. Then there might be a case for doing things like furnaces in chemical plants, which also are moderately big emitters. And then you've got the really quite modest amounts of vent gas that come out of the chemical process. They're well down the priority list. Okay, well down the priority list in terms of spending money to get CO2 emissions down. Maybe in 25, 30 years time, we will be designing plants to deal with this particular issue. But you've got to get used to the idea that we are still permitted to put CO2, small amounts of CO2, relatively small amounts of CO2 into the atmosphere. Okay, because any money we'd spend on stopping this emission of carbon dioxide could be better spent elsewhere. Therefore, nobody's going to give us any. You're not going to get any money to do anything about it. So the CO2 needs to go off through the off-gas incinerator, which will make more CO2, by the way, because it's burning fuel. And so you need an amine that will capture the hydrogen sulfide and not capture the CO2. I can tell you that no such amine exists. No such amine exists. But there is one that will capture a lot less CO2. Okay, so there is an amine that will capture almost all of the hydrogen sulfide and only a modest amount of the carbon dioxide, and that's the one you need to go with. Now, it is not our job to dictate the answer to you, so you've got to go and find it.
Haroon, which one was the one you said earlier?
MEA. Yeah, so I
DEA.
came across, Professor, I came across MDEA, but I never read upon it. Is that the correct one?
I said
No.
there was one amine that would do this for you, right? It's either, well, I've told you it's not MEA.
It's not.
It could be DEA, it could be MDEA, and there are other amines, but
TEA as well, yeah.
So you go in and do a bit of research on that, okay? Okay. Yes. Anybody like to answer that? Why do I need so many pumps around here? Why do I need to pump out of my reboiler and then out of my heat exchanger and into another heat exchanger?
I assumed that there would be considerable pressure drop across the heat exchanger, so I thought it would be
You know
ideal.
roughly what the pressure drop across the heat exchanger is, don't you?
Like
Good
0.2.
answers, by the way.
0.2, yeah, kilopascals. 0.2 bar, sorry.
0.2 bars, yeah.
Sorry, who's answering?
Me, Jaren.
Jeremy, thank you.
Yeah.
You do know what the pressure drop across that heat exchanger is. What is it? Dr. Short gave you a whole list of typical pressure drops.
It was around 0.2 bars.
Well, okay, that at least is in or on the edge of the range you were given.
Yeah.
So I'll accept that. Yeah. Well, you don't need a pump every time you get a pressure change of 0.2 of the bar. Particularly not when you've just pumped the pressure up here. Why would you pump it up again? This is pumping for pumping's sake.
Yeah.
Okay.
Yeah.
You only have as many pumps as you need. You don't have extra pumps. So I don't think you need either of those actually. But there again, you look, where are the temperatures and pressures on these lines?
So if you look at the bottom recovery unit, that's where we mostly did our temperatures and pressures.
Well, you see, that's the problem there, isn't it? Which is
Yes,
There's a great big splurge of red over here, which says,
Oh,
What does it say? You don't need to.
second,
well, it's going to be identical to the first one, isn't it?
first one. Yeah.
Yeah.
Okay. Now,
We
so,
actually discussed that. Yes.
no, right. So you're saying that you've got some temperature and pressure down here, which case I shall look at them.
Okay.
Yeah.
Okay, here's the absorber column operating at, well, now look, you keep giving ranges. The simulator doesn't accept ranges. It says, it either calculates a pressure or it asks for a pressure difference or whatever, right? Ranges are no good.
Okay.
The simulator won't accept a range. It can't accept you being vague. And when next week you'll be trying to do simulations, you'll have to answer the question, what's the pressure drop or what is the pressure here?
Yeah, that's fine.
Yeah. Now, I think you are wrong. And that the pressure here will be higher than that. And the reason that the pressure will be higher there is you have disobeyed me here. Haven't you?
Lock the compressor.
What's in that stream?
Acid gas.
The acid gas.
Well, it's basically hydrogen sulfide.
Oh yeah,
H2S.
hydrogen H2S.
Isn't it?
Yeah.
And what did I say about compressors and hydrogen sulfide?
Because they get damaged by the H2S.
Yeah, they become leaky.
Yeah.
But isn't it only at a certain like concentration, like
Certain
2
composition.
20
Yes, I think
parts
I
per
gave you
million?
20 parts per million.
ppm. Yeah.
Yeah.
That is mostly hydrogen sulfide. It's not the question of 20 parts per million. It's a question of how much less than 100% is it.
Okay.
Yeah. So
Yeah.
you're not allowed that compressor.
Okay.
Now, if you're not allowed that compressor, let's follow that line
Back to the
going
feed.
backwards, right?
Yeah.
In front of the process. What pressure do we have to deliver that stuff at?
Same as the feed.
Same.
Okay.
Yeah.
Again, you're being vague, but let's say 1.6 bar, right?
Yeah.
At the moment, you reckon the pressure here is a vague 1 to 1.5 bars, so that flow isn't going to go, which is why you put the compressor in. But I told you couldn't have a compressor. But what I didn't tell you was that you had to operate the stripper column at 1 to 1.5 bar. If you operated that stripper column at 2 bar, then this pressure here would be enough to drive that hydrogen sulfide back.
Okay.
Yeah. Now, it costs you a little extra money because you're operating your stripper at a higher pressure than you might otherwise like to. But I think I explained to you that for safety reasons, you have to do some things on this plant which cost you some extra money. And here is an example. But you can make that stripper column work at 2 bar, and then you don't need the compressor. And seeing as you're not allowed the compressor, that is what you're going to have to do. Okay.
Yeah. Okay, Ken.
Yes, sir.
This is an air cooler.
Yes, sir.
Yes, excellent. Right, it's the only air cooler on this block diagram. All the other things that are like this are just called cooler. So, are the other ones also air coolers, or is this the only air cooler?
This is the only one. This is the only one that we use.
Okay, unfortunately, you are wrong. Would Haroon, would you like to explain why this is not the only air cooler on your plant?
When let me just look at the.
Okay, no immediate answer. Anas, do you have an answer for us?
There's the other coolers that are coolers as well. I thought they were gas coolers, but
They were
there
gas
was another
coolers.
cooler.
What gas are you using to do the cooling then?
Uh,
Now you see there is a problem here, right? When you say gas cooler, you mean something that cools a gas. Yeah? Is
yeah,
that right? Is that right?
yeah,
Yes, sir.
that's
Okay.
true.
When we say air cooler here, what we mean is cooling with air.
Hmm.
So it's slightly ambiguous, isn't it? Let's change
Yeah,
the
actually,
name to air cooled heat exchanger. Is this
Yeah.
an air cooled heat exchanger? Anas.
yeah, there is.
It is. Right, okay. Are there any other air cooled heat exchangers on this block diagram?
I can't see the full one. Let me just bring up the full one. But yeah, I think there was. I'm pretty sure there was.
Would you like to? I shall now scroll to the left. You shout when you see one.
That cooler there.
What, this one here?
Yeah, that cooler under the waste heat boiler.
Under the waste heat boiler. This one here. How do you know that's an air cooled heat exchanger?
Because I think the red utility was
Utility.
general air utility. Is that correct?
Right, okay. All right, good. And what about this one here?
Which one? I can't see.
The one
Near the
that I'm
absorber.
waving at now. Can you not see my cursor?
Yeah, that one as well. That's an air cooler.
Yeah, that
so
one
you
as well.
call all of
Okay,
them
all right. So
air-cooled
there's an
AC.
inconsistency in the way that you
In the
name
names.
these units. Right?
Yeah.
Now,
Well, that actually brings us to a question that we had for you. We wanted to ask if we can use industrial water instead of general utility air
I tried to be kind and helpful to you, and I can see where I've gone slightly wrong. So what I need to do now is to show you this. Okay. These are diagrams and photographs of air-cooled heat exchangers. You can see similar diagrams in Course and Richardson Volume 6.
Right.
These are what you use when you don't have cooling water. Do you have cooling water?
No.
We don't.
No. It's not available to you. Okay. This is true of the Fawley Oil Refinery, for example. And in hot countries where there's not much water, I think of Saudi Arabia just off the top of my head. Similarly, you wouldn't really have cooling water available, not of the conventional kind. You might have seawater, but that's a whole other story.
Yeah.
You have to use air-cooled heat exchangers. Okay. Notice the design. What kind of air are these air-cooled heat exchangers using?
Ambient air.
Ambient air. What does ambient mean?
So at like temperature of 25 degrees and pressure of 1 atmospheric pressure.
And where does it come from?
Nitrogen and oxygen.
No,
So-
where does it come from? What
Atmosphere.
pipe do you take it out of?
Wouldn't it straight come from the atmosphere?
It comes just from the atmosphere. What's the cost of taking air from the atmosphere?
Nothing.
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 Yeah.
What's the cost of plant air? We
Nothing.
didn't give you a cost of plant air. Maybe we should do. I don't know.
Uh,
What do you think the cost of plant air is?
It was. I think I saw it was like £3 or something.
It's not. It's not free.
Yeah, it's not free. Yeah,
It's not free.
yeah.
And what's more to the point, there's a limited supply.
yeah.
So these air coolers or air-cooled heat exchangers, they do consume something. It's called electricity to drive the fan
Yeah.
that makes the air from the atmosphere go through the tubes. You can see some thin tubes here, right? And then out the top, and then it goes upwards into the atmosphere, right? That's an air-cooled heat exchanger. All of the places where you would otherwise be using cooling water, you are going to use that kind of unit, right? Including the one I was looking at across here, this air cooler. So that connection is wrong. You don't use general utility air at all in your process. Okay, it is available. Okay, for general purposes, which are mostly to do with driving pneumatic tools. Okay, so you need it to be available to do certain things on the plant, but it is not going to be part of your steady state process.
So you're suggesting that we use instrument air then, as opposed to general utility air to cool it down?
No. Where did we just say the air came from?
The ambient
Ambient.
Oh, okay.
Yeah, sorry, sir.
From the atmosphere.
The sprays.
The only thing that you connect your air-cooled heat exchanger up to is the electricity
It's the fan that runs it.
Ah, okay.
that runs the fan. Okay.
So I got one question. So on top of our block flow diagrams, do we put a line called electricity and then connect it to the...
Well, you could do, but I think that's probably going a bit far.
Okay.
I think that's optional.
Okay.
Are you a 6-person group?
6-person group, yeah.
Yeah, well, the utilities engineer will be drawing a utility flow diagram that will show all of those electricity flows. So there will be a diagram that shows that in the final report.
Okay.
But I have seen students do it. It's up to you.
Okay.
But once you put one electrical supply in, you've got to put them all in.
Yeah, for the pumps and... yeah.
Again, your off-gas incinerator won't be using general utility. You just take air out of the atmosphere.
Right.
Now, you may use a fan to make it go in, or you may use natural draft. So, in fact, you've got a chimney. Well, you think you might have a chimney, but notice that this stuff that comes in here and all that stuff that comes in there, it goes nowhere. It disappears into the black hole.
Could be vented out.
Well, you need
It should go to a stack.
you need
Yeah.
to show that it's
Yeah.
going out of that unit and then it's going in the end. You then got to build a chimney, right? That
Yeah,
stuff's
right.
going to be very hot.
Isn't
you
a stack
can't just
basically
let it
chimney?
Flow out, to where operators are going to be standing. You've got to put it up a chimney and that's one of those reasons why you have chimneys is to make sure that hot gases get released at a safe height.
Right.
Now, you may not regard a chimney, or actually in chemical engineering we call it a stack,
Stack, yeah.
as being a piece of chemical engineering equipment, but it is. And you'll find the design of stacks in Coulson Richardson Volume 6. Okay?
Yeah.
Right, we've got to 240, and I like to try and leave you space to ask some questions. Okay, if not, I'll say some more things about block diagram. But let's go around the group now. See if you've got any questions. And the person who happens to be top of this at the moment on my screen is Jason.
Yeah, so one question I had was, in the process brief, we had the cost for the catalyst.
Yeah.
So would that be like a generic cost for example, for the aluminium, for for the hydrogenation reactor catalyst. I had a bit of confusion with that.
Well, you've only got one. Oh, right. Okay. So there are two catalysts. That's true.
Yeah.
I'll look at the brief, but I think that's probably the sulfur making catalyst.
Right.
Yeah. I'll get back to you on that.
That's right. And also, sir, one question I had was, after the reactor furnace, am I correct in saying that condensate comes out as the utility? So you got the flue gas entering the reactor furnace with the air.
What here?
So there, yeah, for the whole equipment. So you got the flue gas entering, and you got the ambient air entering as well. So I was wondering, as utility, would the condensate come out? Condensate, sorry.
Well, no, because you're not putting steam in. You can only get what normally when people say condensate,
It's for steam.
they probably mean steam
Steam, right.
condensate,
Right.
which is water,
What?
quite pure water. So return it to that. You only get condensate if you put steam in, and steam doesn't mix with something else.
Right.
Otherwise, you'll get contaminated stuff, right? Now, the temperature here you've got as 1,000 to 1,200 Celsius.
There will still be gas.
You're going to need a much bigger pressure than 3 bar.
Yeah.
Okay.
Mm-hmm.
To condense water out at that temperature. It's above its critical temperature. It won't condense. I don't understand how you got condensating on the line.
Sorry, sir.
However, it does point out another problem, which is what's the pressure then?
1.5 to 1.65.
And what's the pressure here?
3 bar. So
How
pressure
did that
increase.
happen? How did the pressure go up? Now,
I assumed that it was an exothermic reaction, so expansion of gas would lead to a high pressure.
Increase pressure.
Yeah.
okay. Now look,
Reduce pressure. Reduce pressure.
look. One of the battles of becoming a chemical engineer is you have to switch your thinking, if appropriate, from batch processing to continuous processing. If you have a gas in a closed vessel and raise the temperature, the pressure goes up.
Yep.
If you have a gas in a continuously flowing process and the temperature goes up, the pressure doesn't go up, but the volumetric flow rate goes up. Okay, because it's an open process. Both ends of the reaction furnace are open to flow. Okay, so the gas expands.
Mm-hmm.
The key process is it closed, in which case the volume's fixed, or is it open, in which case the pressure's. And this is well in the sense that you've got a pipeline with nothing blocking it. Nothing blocking it. It is an open-ended vessel. Okay. So how did the pressure go up? Well, the answer is it can't. The only way you can increase the pressure in a continuously flowing process is to use a pump or a compressor.
Yeah.
This is a gas, so you can't use a pump. And this is a gas with hydrogen sulfide in it, so you can't use a compressor.
Right.
So the pressure can't do that. Now that's problematic, isn't it?
Mm-hmm.
Yeah.
Because it means that the pressure here, therefore, has to be less than 1.5 to 1.6 bar. And that means you have to alter all the rest of your pressures.
Yeah.
Now look, you are behind the other groups. You have not put temperatures and pressures on your lines. I'm not saying the other groups have put temperatures and pressures on every line, but they have put temperatures and pressures on very many more lines than you have. And until you try and put temperatures and pressures on these lines, you don't come across this kind of problem. And this is a real problem. You've only got this amount of pressure to drive the gas all the way through the process. Okay? You must get the temperature and pressures on here, even if they're wrong. I don't mind if they're wrong. We can talk about it if they're wrong. I can find out why your thinking is erroneous. Or if I think they're right, but they cause a problem, which I'm predicting they will, then we can discuss how to get around the problem. Okay? What I will not do is dictate the answer to you. Whose question was that? Was that Jared or Jason? I can't remember.
Jason, sir.
Jason, okay. Jared, do you have a question?
No, I don't have any questions. No.
Okay. Ken?
Is regarding the quench column. Yesterday you mentioned that is a quite updated version, information. So we went to look out for any more references regarding using the quench column, but all of them,
here.
yes,
Okay.
on the score process, but all of them they mentioned using the quench column.
Right.
Okay. Would that be a problem if we still use it?
No, it's not. It's not a problem, but I just want you to understand there are two ways of doing that. I think there might even- This is one way. Another would be to use a partial condenser with a vapor liquid separator.
Okay.
What's
All
the advantage
quench
of?
column does is bring the temperature down to virtually to ambient.
So wouldn't it be expensive to have two equipment? Like capital
Well,
cost wise.
You've got two equipment.
Wait, so,
And then you've got another cooler here as well.
oh yeah,
So you've got three equipment,
yeah. Sorry, yeah.
and I'm suggesting two.
Two.
So
Yeah, sorry.
am I winning?
Yes.
Right.
Yeah.
Now, look, there are times when you would do that, and you would do that if you were desperate to have that quenching happen quickly. But you're not desperate to have that quenching happening quickly because otherwise you wouldn't have the waste heat boiler. Okay, so you're apparently quite happy for these gases to go through that waste heat boiler, take several seconds over it, and then quench it. If you really needed to quench, you need to quench straight away. Because quenching is all about stopping chemical reaction.
Yeah.
This is a catalytic reactor. You need the catalyst to make the reaction happen. When it comes out here, the reaction has stopped. You in a leisurely way take it through the waste heat boiler, and then for some reason you then do something sudden to it. Well, why? There's no reason why you need to quench, and therefore a partial condenser and a vapor liquid separator will do the job, and they will do it slightly more slowly in terms of time and flight of the gas, but you have no need to do that really rapidly.
Right.
Okay.
Mm-hmm.
This may be a convenient and cheap way of doing it in the lab.
Okay.
In the lab.
Which is why it turns up, or on the pilot scale, which is why it turns up in all the literature, because the literature is based on a pilot experiment that they've done at some stage, and I really just think that. But this would work if you want to build it. That's your choice.
Okay.
So if we go with that, we just remove the quench column and the cooler.
And the pump as well.
No pump.
Yeah, and the pump as well.
Well, you don't. It just goes straight through into a vapor liquid separator. The gases go into the absorption column, and the liquids go down this line here.
Yeah, just triple. Yeah.
Who was next? Was that Harun that asked that question?
No. Well, I'd like to ask a
Harun, do you
question.
have a question?
Yeah. Well, the group and I were discussing the pressure which air goes in. Does it have to be the same as the feed? because we were thinking of putting a valve in front of the air before it went in the
No,
burner.
but the air's not coming from there anymore, is it?
No, it's ambient.
Okay. But
Okay.
fundamental truth in fluid mechanics is you can only mix fluids when they're at the same pressure.
Pressure. Okay. I'm guessing the safer option is to make the air the same pressure.
You can do it by increasing, if you've got two streams at different pressures, one of which is a lower pressure and the other which is a higher pressure, you can either raise the pressure of the low pressure one using a pump or compressor, or you can lower the pressure of the high pressure one using a valve. Valves are much cheaper than pumps and compressors, and anyway, you're not allowed to use compressors.
But since
And,
we aren't allowed to put in valves in a BFD, how would we show the
But
pressure?
you are allowed to put valves on a BFD. Who said you couldn't put valves on a BFD?
Oh, okay.
What you were told was you can't put control valves on it.
Oh, right, okay.
Yeah, important valves that drop the pressure are allowed on a BFD. Okay. Now, I don't think you need to show a lot of valves on a BFD. But what you've got to realise is that the valve will be there, and therefore, if you mix two fluids at two different pressures, if you then show the outlet pressure being the lower of the two pressures, it will be understood that there was a valve.
Okay.
Okay.
Also, how do we assure that a 1 to 2 reaction ratio happens?
But using your control system.
Using, sorry?
Your control system.
Control system, okay. And
Isn't that what control systems are for? Making sure that the process operates as you intended to.
yeah, I also saw a diagram that had the feed connecting at 2 points. So for only like for a 1 to 2 reaction to happen, so like the feed was connecting past the burner and also into the burner to guarantee this.
But you can do that provided the total flow rate that you put into the two places adds up to be exactly what you need to get that ratio.
Okay. Yeah.
Anis, any questions?
I think you've answered a lot of them. Maybe just one question about you see the first heat boiler, the HP steam coming out of that. We're thinking of using that to heat up other reheaters. I just wanted to ask, as a form of heat recovery, how many reheaters will be able to
Heat up.
so at the start of the process, the waste heat boiler.
Right. Well, the first thing to say is this. You don't ever do that. You don't ever use your own steam. What you do is you put any steam you generate into the steam main, and you take steam from the steam main. This has the advantage that when you start up, okay, you've always got connections to the steam main that allow you to run any unit in any order. Also, if you have a problem with the boiler, it's the utility manager's problem to supply you with the steam you need and not your problem. Okay? It's okay because for every ton of steam you put into the steam main, the utilities manager will give you the credit, and for every ton of steam you take out, he or she will charge you.
Yeah.
So it makes no difference to you that you never use your own steam.
No,
Okay?
so you just save it.
The next thing to say
steam
is, can you use steam in all of your reheaters? Well, you're the designer, you work it out.
Yeah. Depending on the requirements of how much steam they need.
Well, I think it's more a question of what temperature can the steam produce. And what temperature do you want? Now, I notice that you have not decided what temperatures you need in your catalytic reactor. It's not on the block diagram.
Okay, so I know we did a mistake regarding that, but as Jeremy mentioned earlier before, most of our temperatures and pressures are on the
Oh, below.
On the bottom. Okay, well, let's go down here then.
on the
Yes,
second.
thank you for pointing that out. I was just realizing that myself. So let's have a look here, right? So here you've got your reheater, or one of your reheaters. Let's get that out of the way. Wait a minute. I can't get that out of the way because I'm in the wrong software. Never mind. So here's a temperature. This catalytic reactor is operating at
460.
460. Wow.
2573.
I don't think you've got any steam that will condense at a temperature above that.
Yeah.
So how do you reach 460 to 573 using steam?
We'll have to use like
Can't.
flue gas. Yeah, we can't, yeah.
Yeah, flue gas.
Flue gas or something.
Now, when you get to this kind of temperature here, it maybe is almost possible, depending on what pressure of steam you've got.
Okay, okay.
But you've got the information to what steam.
Yeah.
Okay. Christian, did you have a question?
No.
Okay. All right. Well, I think we've run out of time. You need to make a more rapid process on this. You really got to take on board what's been said today. Improve your block diagram. Get it to either myself or Dimitrios later in the week. Get some more feedback on it. Otherwise, you're going to be falling behind. Okay.
Mm-hmm.
Get your component list sorted out, and then there's another list that I published under week 2 in Surrey Learn. Make sure you've read that list as soon as to do, and get them done. Okay, thank you very much for your attendance.
Just one more question. What are the deliverables for next week's meeting then on Tuesday? Is it just
Read the list in Surrey Learn.
okay? All right.
But obviously a considerably better block diagram
Okay. Yeah. Sure.
and a better component list.
Okay.
Plus the things that are in under week 2.
Yeah.
In Surrey Learn.
That's fine.
Yeah.
Okay.
Yeah.
Thank you very much.
Thank you.
sir.
Bye.
Right.
Oh, me.
Yes.